you to accept the invitation. If you don't accept the invitation. Okay, I'll check again. I can have you again. Have you all received an invitation to SLAP?
Yes.
Okay.
All right, great.
What? Okay, can you send me your mail again and then I'll try and add you again because.
Okay, so let's start. And where we ended last time. So we just essentially try to get to the qubit space for the purpose of mapping to qubits our fermionic degrees of freedom, our Hamiltonians and states. And we started looking into a single qubit. What is essentially the way to represent the single qubit state? It's very simple because it's a two-level system. System being and level 0 is like this, and system being at level 1 is like this. So those are two orthogonal states, 0, 1, 0, and then any, like let's say I, that's the I being either 0 or 1, right? So those are the two states of the qubit system. And we also talked about that any single qubit operator can be essentially, can be written as a linear combination. Let's say if we have an operator that acts on a single qubit, one qubit, then it can be written as a linear combination of Pauli matrices or Pauli operators. K goes from, let's say, 0 to 3. And we define what these Pauli matrices are and their properties. Now, the only thing that I guess I would like to add to this before we go to the multi-qubit case, which is more interesting, of course, is that one way to get these coefficients potentially in the one qubit case, and that will be also in the multiple qubit case as well, that these coefficients, because this is kind of element of a linear space, and this is the in this linear space are kind of operator basis. We could define inner product, and through inner product we can obtain the coefficients. And the inner product in this space of operators can be written as a trace of essentially sigma k dagger O divided by the dimension of the space. Dimension of the space. Dimension of the space is in the case of one qubit is 2, right? And in the case of this is for one qubit. For one qubit, and for multiple qubits, it will be 2 to the power of number of qubits. For one qubit, it's n qubit is 1, right? All right, so this is very natural structure that allows you to get the coefficient in expansion of any operator in terms of Pauli basis, essentially. Okay. Now, I guess the one more thing that is of possible interest is that potentially, if you have a state of a single qubit and like you want to know the expectation value of any operator, then this could be obtained by using linearity of our space as this expansion. A goes in 0 to 3, and here we use sigma k expectation values, right? And the first term is trivial since the sigma 0 is identity. Then this expectation value of the function with itself will be 1. So then we have C0 plus sum over C k, where k goes from 1 to 3, sigma k. And then knowing only expectation values for the sigmas, we could get essentially the expectation value of any operator, right? So the expectation values of the sigmas, they characterize essentially the state fully, because using those expectation values, you could obtain expectation values for any observable you want, right? And so then as probably one of the homeworks, it's easy to show that this sigma k sum squared, this k goes from 1 to 3, will be equal to 1. All right. So what this means, this is like an exercise. If you put one qubit state that isn't generally, the qubit state is in general alpha 0 plus beta 1, right? For any alpha and beta that, of course, satisfy normalization. Right, so then this will be true. And that sort of tells us that we could represent, since these guys represent the state of the qubit, we could represent it as a unit vector in the 3D space, where each coordinate is just say sigma x expectation value, sigma y, sigma z, let's say expectation value. This one is sigma y expectation value, and then the state will be a vector here on this sphere with the length 1. Okay. So that's another way to characterize the state through expectation values of Pauli matrices. Okay. And everything is very actually geometrically nice in the single qubit case, but the power of quantum computing, of course, is not in the single qubit case. You need to go multiple qubits to see it. Okay. All right, but algebra is very easy and straightforward in the one qubit case. All right, one last thing would be to explain a little bit how do we modify. We will be talking about unitary transformations in a moment, because it's related to what quantum computers can do, right? Because in general, quantum computers, they operate with unitary transformations, because unitary transformations don't change the norm of the vectors, states, and the states encode information. So you don't want to lose information, you don't want to lose norms. Therefore, the main activity will be using the unitary transformations. And then just to finish one qubit case, one could ask the question, what is the general unitary transformation that we could write for a single qubit case? And essentially, if we have some unitary that is acting in one qubit space, and we start with, let's say, with 0 state, could start with state 1, doesn't really matter, with some state. So we obtain some general state Q, how do we really parameterize the most general, in the most general form, this unitary transformation? And it turns out that there are multiple ways to look at this operator, and one of the, I guess, one of the somewhat simplest maybe way would be to just write it as a single exponential operator, where we have the following components. And I will explain in a moment what they are. Let's say we have n, here the vector, and the sigma is a vector. Okay, so this is what U1 qubit is. And the idea here is very straightforward. First of all, any unitary, whether in one qubit case or multiple qubit case, it's always can be parameterized as an exponential function of the anti-Hermitian so-called generator, right? So A here, anti-Hermitian. Why do we need anti-Hermiticity here? Simply because we have for any unitary this condition to satisfy, right? Therefore, if we apply this dagger sort of condition on this exponential function, then we'll get dagger in the exponent, and that should be minus a. So that guarantees that we will have a cancellation between u and u dagger, right? Because if you multiply this now with the exponent of a, that will give you identity. So therefore, whatever we have here, it needs to be anti-Hermitian, and it is, because one way to get anti-Hermitian operator is to take Hermitian operator and multiply by I, right? So this is the I, and this part is Hermitian. Okay, and so what this part is tau is a parameter, and then n is just three-dimensional unit vector, right? So the norm of n is 1. And then sigma is just a short notation for a vector built out of these operators that we introduced, Pauli. You can think of them already as matrices. So this is just a short notation for a sort of an inner product, which would be a linear combination of sigma, let's say k and k. K goes from 1 to 3. I will switch between 1 to 3 and the XYZ, but yeah, the idea is hopefully relatively clear. So this is the inner product, right? And what we have here, since we have normalization, this vector effectively, again, is, you could think of it as a vector on the unit sphere in the 3D space. And then what's happening here by this unitary transformation, we effectively rotate the state around a chosen axis, right? N is defining this chosen axis, and we rotate by angle tau, okay? So we have a freedom to choose n, and we have a freedom to choose the tau, okay? Now, there are two parameters here and one parameter here. So generally, this is giving us three parameters. And that's enough to essentially describe any rotation of the single qubit state. Actually, what we will get is that the qubit state itself has only two parameters that are important for physical quantities, right? But we have three parameters, so one will just will contribute to, or all of them actually contributing to the global phase, which is not after all important, okay? But this is the same type of rotation that people use for the solid three bodies in the classical mechanics. They also could be used here as a kind of rotations in a single qubit case. And another, I guess, mathematical fact you could look up and will be somewhat important for us in the future is that these unitary rotations that are now described by tau and n technically. So these unitary rotations, they define, or they are part of the mathematical construction that is called group. And not only them, but generally any unitary is a part of the group, because what group is the set of objects where you can essentially multiply objects, and you will not get outside of the space of these objects, right? So these unitaries, you can multiply them and you get other unitary back always. And this multiplication is, in this case, just application of operators one after another. And it's non-trivial because you could sort of potentially get outside if you multiply objects. Let's say if you are dealing with negative numbers, as an example, -1 times -2, you get outside of these objects because you get 2, right? So you lose the negativity. So if you were trying to organize a group out of the negative numbers, then it won't work, at least using the normal multiplication. It will work using the addition instead as an operation, right? So that will work. But with a normal like multiplication, it won't work. So we get outside of the objects that we want to create a group with. And with in the case of unitaries, using the operation that is multiplication of operators, it does work. So we have a product of unitary again unitary that can be easily shown in linear algebra. Probably you've done that. And here it's a nice property because no matter how many unitaries you apply, you still guaranteed that it's still some kind of unitary that can be parameterized in this manner. Okay. Now there are a few other conditions for the objects to be a group. One that is quite important is that every element could have an inverse, right? And for unitaries, it's always the case. For every unitary, you have a dagger, and there is need for the so-called element that is identity. And in this case, we have identity operation that is just take any tau to be 0. So then angle 0 rotation would respond to the identity element. And identity is defined by the condition that you multiply any unitary multiplied by identity gives you back the same unitary, right? So no matter whether you multiply it from the right or from the left, it just gives you back the same element, right? And there is yet another condition for the group. It's associativity of this operation, but we know from linear algebra that there is associativity of matrix multiplications. So associativity means is simply A times B times C. If you put the brackets like this, it's the same as putting brackets like the other one, like this. Okay. And so this usually is taken for granted, but it's not always the case. The one simple case where we could define operation that is not associative could be a vector product of three-dimensional vectors. But if you want even simpler example, we could again do something with numbers. And let's say if we have like two numbers m and n, right? And there is some special operation that we wanna maybe base our group on, because all we need is some binary operation that is associative. And we define that operation as having minus m, right? So this is how we define the operation here. And you could check with put in some numbers like 1, 2, and then if you, for associativity, you need 3 numbers, 1, 2, 3, let's say, then you could see that this operation is not associative, so it won't work. Now, something even closer to what we'll be doing, it turns out that if you try to define a product between, let's say, 2 operators as a commutator, it's non-associative as well, right? So A, B, and the commutator with C is not equal to the situation where we do them, let's say, A with commutator B and C, like this. And so this is not the case. And we'll see what do we have for the commutators as a substitute for associativity, but commutators are not associative. So you cannot build a group based on the commutators. Returning to our unitary case, so it's a group, it's nice, and we will be able to use that for our considerations. Okay. Any questions so far? So straightforward. Now there is a mathematical name for this group for a single qubit. It's called SU2 group. And that's a special unitary group of essentially it's a, you could think of it as any two-dimensional unitary matrix with a determinant 1. And why is it special? Because not every unitary 2x2 matrix has a determinant 1. In general, it has a complex number, right? With the absolute value 1. But these unitaries, they have as well kind of determinant equal to 1. And that's why they are SU2. And it turns out that we will be talking about this more extensively. So these are so-called example of Lie groups, groups of with the continuous parameter. And the continuous parameter here is tau, and well, the way we kind of could think of about the n, right? So n is the unit vector that can be parameterized by 2 continuous variables like azimuthal and polar angle. And so the nice thing about all this is, on the one hand, these Lie groups are kind of more complex than the groups that you may have seen in, say, point groups in the spectroscopy of molecules. But the nice thing about the Lie groups is that because of the continuity of parameters, you can differentiate the elements of these groups. And what this means is that if you want to find a special rotation that makes the job of rotating your qubit to a particular state, that usual problems are you want to find the unitary that rotates the state, let's say simple state, into a state that has a minimal expectation value of some operator, right? So if you have Q, here expectation value of some operator, and you want to find the unitary rotation that does that, minimizes expectation value. So if you don't have a group that is continuous, then you need to just go element by element and find what is that unitary that does what you want. But if you have a continuous group, then you could use gradients, right? So, and that's very big help. Of course, until you realize that gradients usually lead to local minima, and then there is additional problems or small gradients could happen as well. But in general, it's more helpful to have well, gradients at least at your disposal. And you need to solve, of course, a global minimum problem, but still, it lets you go somewhere. So these Lie groups are going to be very much in use in our course. And another construction that will be very convenient for studying the Lie groups is Lie algebras. And we already seen that connection, because what is happening here generally on a very kind of simple intuitive level, you could think of Lie group that we mostly will be dealing with is the unitary transformations, and the Lie algebras are going to be the generators, the exponential part of that operator, right? It's somewhat similar to things that you already seen in physics, which is like, let's say, translation of some operator of translation, where the generator of translation is momentum operator, right? Or rotation, angular momentum, right? So any rotation essentially by angle phi, let's say around the z-axis, will be exponential function of I phi multiplied by angular momentum LZ, right? Or translation by delta will be exponential of I delta momentum along the, let's say, x coordinate, right? So all those are the examples of Lie groups with the corresponding Lie algebras, which is algebra of generators here. And turns out that looking at algebra is very helpful to study the groups. That's what was discovered by Sophus Lie. Sophus Lie, Norwegian mathematician. And yeah, that's why it's like these groups and algebras are called by his name. And in the particular case of, I guess, single qubit, it's easy to illustrate how the construction of Lie algebra comes in, because we already saw that we have all these sigma generators in the exponential function. And we also saw that from the elementary quantum mechanics that sigma x, sigma y gives you 2i sigma z, right? So these operators are connected with the commutation relation. And therefore, essentially, what one can do is to construct a linear space based on the sigma x, sigma y, sigma z as our basis vectors, right? So they're operators, but we're considering them as basis vectors because essentially any operator that is traceless, in this case, for a moment, this is like a condition, could be written as a linear combination of just this three, right? Sigma k, k here 1 to 3, and in order to call this algebra, we need now to define what is the vector-vector product. And naturally, vector-vector product could be the commutator, right? So this is what is the element that makes this linear space to be an algebra, okay? And it's called Lie algebra because also SU2, the notation here could be a little bit confusing, but usually the group as kind of Lie group is called with large letters, SU2, and the corresponding algebra with small letters, okay? And so this is SU2 algebra. Now there is a, what do we have for this multiplication? As I said, it's not associative, meaning that we don't have the associativity in this multiplication based on the commutators. But that's okay, because algebras don't generally require associativity of the multiplication. We have instead something that you may have seen somewhere else, so-called Jacobi identity. And that's the alternative to associativity. Jacobi identity is simply easy to write. One can just simply do this using the circular permutations. So let's say we write these three elements like this, and then we start shifting them, sigma y, then sigma z, sigma x, plus another shift, which will be sigma z, sigma sigma x, sigma y, and that must be 0. So from this, you could see that actually the associativity will be violated if you insist on so-called Jacobi identity. But Jacobi identity is something that Lie algebras generally require as a part of the definition. With that, now the only hopefully last thing I wanna mention here, if you look this up, there is a difference in physicist and mathematician notation about the SU2. The difference is that okay, in the case of mathematical literature, what they prefer to have is generally real constants. When you do the commutator of elements, you potentially could have a linear combination of elements from the set, but the coefficients here are going to be like, ideally, if you could make them real, then it's kind of more, I guess, concrete information about algebra. The coefficients could be complex, but if you don't have you don't have need to make them complex, you kind of mathematicians prefer to make it kind of keep them real, so that those are different algebras with real coefficients and imaginary ones. So therefore, we know that commutator of Hermitian operators is anti-Hermitian. Therefore, we have the I here. But if we make the definition of our essentially basis vectors as I sigma x, those are anti-Hermitian operators, then we will have a nice closure in the sense that the commutator of Ix with I sigma y is just equal to 2 I sigma z, right? So we will call these guys our basis vectors, and they will have a real coefficient. So that's what mathematicians prefer to have. And physicists, of course, they prefer to work with Hermitian measurable operators of observables, and then you get in the price to pay for this that the coefficients are imaginary. So there is this little difference. How do you perceive those? What is your basis vectors in this algebra space? But other than that, generally speaking, these algebraic structures are very useful because you exponentiate them and you get the group. Now, there is a little bit of a caveat there, which we'll probably talk when it will be important. But the caveat there is that not every exponentiation could generate the entire group. So there are some, one needs to be careful with what you exponentiate. And that's a topic of a kind of a little bit bigger discussion. But at the physical level of accuracy, right now, where we're working with so-called compact groups and compact algebras, then that is totally fine. You could exponentiate any linear combination and you generate the group. There are some problems with this procedure when the groups are not compact, but on a very, again, a vague and physical level of accuracy, I guess, or rigor, you could think of compact and non-compact as something that changes the norm or doesn't, right? And so all unitary transformations are compact, essentially, and so we're fine by exponentiating the algebras. So usually that doesn't lead to any problem. Right? I'll illustrate later the situations where one needs to be careful how to exponentiate algebra to get the entire group. All right, so that's essentially one qubit case, single qubit case, which is very nice and simple. And now we could talk a little bit more about the more interesting case of multiple qubits. Raise this, and while I'm doing this, if you have any questions, please ask. People online as well. So in multiple qubit case, it's kind of easier probably to illustrate using 2 qubits. What's happening when we have 2 qubits? The space where things are happening, if we say there was a linear space of a single qubit, where was like the basis of that single qubit space was with these 2 states. Now with 2 qubits, we are working in the tensor product, which is not surprise because that's what makes quantum mechanics hard. When you have more particles, then your wave function starts living in the exponentially large space, and that exponentially large space would generally be connected to the mathematical concept of the tensor product of spaces. And that tensor product will now have 4 vectors: 0, 1, 1, 0, and 1, 1. Okay, so these 4 and general vector or general state. You want general state. 2 qubits will be a linear combination of ij, Cij, right, where I and j go from 0 to 1. Okay, so, and of course, this could be generalized to n qubits, where it's a tensor product of n linear spaces, and then the function of n qubits is just as we know it, a linear combination of Ci to j here from I, j. Generally, we have in this construction 2 to the n qubit states. Okay. Yeah.
The 2 qubits, the
Mhm.
summation is 0 to 1.
For each index, right? So each
It was that 1, right? From
0 to 1, yes. So yeah. All right, so it's to go over the entire set. Okay, and then what is interesting, like I guess what mainly people are interested in the situations of n qubits, there are a few reasons for that interest. Is the concept of entanglement. Right? So entanglement is the situation where your 2 qubit state, if you don't have an entanglement, it could be really written as a single qubit tensor product with another single qubit, maybe a different state, but you sort of organize the factorized state, which is just 2 single qubit states, and this is no entanglement. It's a simpler situation, simply because as we talked, I guess in the case of n qubits, it's right away clear that here we have 2 to the n qubit states, but if we generate so-called product state, no entanglement, product state for the n qubits, it will be product of 1 qubit states, and we know for each of these, let's say for each of these 1 qubit states, the amount of information that we have here is just in 2 coefficients, right? 2 complex numbers plus the normalization, and then you remove the overall phase, and that leaves us 2 parameters essentially. And if we have n qubit state, n qubits, then it's 2 to the n qubit parameters that you can encode in this product state, right? Side product. And then this is not much information-wise. Therefore, usually such states are not of big interest, and more power actually comes from having entanglement, where this sort of factorization is not possible. You could already see that in the situation where it's a general combination, which is not a product state, we have a lot of coefficients. But I guess one of the original motivations for excitement about the entanglement was this Einstein-Podolsky-Rosen experiment, where there was constructed the so-called now Bell pair of states of the state, let's say, that is entangled, cannot be factorized. We'll discuss why, right? So this is let's say Bell pair, right? So if you construct this state, then you could simply model these qubits as photons. Let's say with the photons, it's you could use polarization, horizontal or vertical, to encode 0, 1. And so then you could send one photon to the Mars, and another stays in Earth. And then if someone measures this first photon, and the measurement will collapse it to, say, 0 state, then you know that, or probably it will make more sense to do the collapse on the Earth. Then you'll know what will be the kind of the photon on Mars, right? So it also will be 0. And the other way, if you get the 1, then you know that the other also will be 1, the one that went to Mars. So this is not the case if you have a product situation, that no matter what this one qubit state in the product state is, this one could be completely independent of this one. And learning about this, I will not give you anything about any information about this if you, of course, you sort of don't know it already. So in classical terms, sometimes people, I think John Preskill has this nice analogy that you could think of the measurement as almost like learning something or reading a book, right? So if your qubit could be connected or compared with one page of the book, right? So if you have a product state, you have a classical book where you read page after page after page, right? But if you have a quantum book, so depending on what you read on the first page, well, and then it could be probabilistic, and then the second page will be different depending on what you read on the first page, right? And that is a quantum book, sort of, which has more information encoded. But once you start reading, depending on how you start, how do you read, and where what information you're getting in each book, in each page, and the result of the next measurements could be different, or different pages as well. The reading of the different pages will be different, right? So this is the original, I guess, quantum information, reasoning, or motivation behind the excitement of for the entanglement. In our case, when we talk about, let's say, modeling the quantum wave function, people usually stick to the fact that well, more entanglement in the more information could be encoded with the entangled state, and product states are simple and don't really carry much information. So therefore, if you're trying to construct a wave function of the complicated system, you would like the unitary transformations that you will be using, they generate entanglement relatively quickly, right? But unfortunately, I don't think It's already been shown in several problems that just entanglement by itself, you could quantify it, but it's not necessarily more entanglement gets you closer to the right answer, because the space overall is very large, and what the true eigenstate will be, it could have more entanglement, less entanglement. It may depend. Plus, one other important aspect of the whole entanglement story, it's entanglement depends on what do you choose as your single particle basis, meaning that you could define sort of one particle states differently in the problems, and entanglement could change because of that. But once we are in a certain basis, of course, then entanglement is kind of could be unambiguously defined in this situation. To give you, I guess, very simple example, one can, of course, see that if we are dealing with a potential product state that was done by generating, let's say, this for the first qubit, product with let's say 0 minus 1 for the second qubit. So clearly, if you, this is a 2-qubit state, if you open the brackets and write this sum as a sum of states, then there will be some coefficients like 1/2 for 0, 0, then of the 0, 1 plus 1, 0. There will be 2 minuses and 2 pluses. Let's see, minus 1, 1 and minus 0, 1 plus 1, 0, and everything with the 1/2. Right. So technically, if someone gives you this type of state, you may wonder, okay, this looks like a state with entanglement, but we know where did it come from. It came from the product state. Therefore, there is no entanglement. There is a way to make a linear combination of a single qubit states and write it as a product, right? And of course, when you work in with multiple qubits, there is always this question: if someone gives you the linear combination of products, how do we know that it's not a single product? And there is a relatively straightforward way of answering this question. That is, no, there are actually few ways to do that. I will, for now, just show you something that is called Schmidt decomposition. And if needed, we will also discuss at some point the formalism that involves the density matrix, but not to introduce new quantities without necessity. I will just explain this using Schmidt decomposition. And was just wondering, maybe everybody is familiar with this or no? Okay, some are familiar, some are not. But the idea is relatively straightforward. What one can do is, let's say, if we have a wave function that is written as for 2 qubits, right? And then we'll talk about generalization. For 2 qubits, ij, we have Cij, ij, right? This is a 2-qubit state. And then all you need in order to decide whether this is actually presentable as a product, single product or not, maybe single product of one qubit states, right? With some coefficients. All you need is taking this coefficient and representing as matrix. Okay, so clearly with two qubits, one index and another index, I and j. So this is 2 by 2 matrix, right? So 0, 1, 0, 1. So this is C0, 0, C0, 1, C1, 0, C1, 1. And then you do SVD, single value decomposition of this matrix. Generally, it's this construction where the U and V are two unitaries and the sigma is non-negative diagonal matrix in the quadratic case. But why do we talk about SVD here instead of, let's say, diagonalization? It's just because SVD is more general procedure, and we sometimes need this if, let's say, we go to the more general case, 3 qubits, right? So then psi for the 3 qubits generally is sum overCijk, here ijk basis. And if you want to know whether there is a entanglement, so you could start with doing SVD of theCijk, but now you're constructing this as a rectangular matrix. Let's say you want to know whether I can be kind of presented as a single qubit, and then Jk could be some state with potential entanglement, but you want to see whether I could be disentangled from this. And maybe like a simple question could be, can we do 1 qubit for the first, I guess, some state times potential state of 2 qubits, which could be entangled or not, we don't know for now. But for answering this question, we would consider Ci and Jk as a matrix where I is one index, say columns, and Jk are rows, right? So then columns and rows will be like, for the columns we'll have 2 entries, and for Jk we'll have 4 entries. Therefore, with the matrix will be some sort of rectangular matrix like this. And of course, then diagonalization is not possible. So SVD, though, still possible. Therefore, SVD is used in this context to see. And what are we actually getting from SVD? From SVD, we're getting the essentially representation of C matrix Cij. Let's say, again, going back to the quadratic case, Cij, it's represented as a Uik, sum, sorry, not sum, but sigma Kk, it's diagonal matrix, and then V Kj, right? And so it's a summed over case, K index, right? And the question about the, I guess, entanglement comes to only the question whether we have a singular value or multiple, right? So if we have just imagine only one non-zero singular value, then the sum will have only a single term, and one can simply present indeed this linear combination as a product. So the way to do it, the way to present this as a product is, we know that original sum is, let's just write it down, assuming that k is equal to 1. Let's say there is only a single k that has non-zero singular value, and then we will have sum over ij Cij will be substituted by u I k. Let's keep it k, but it's only one value, so we don't have summation over k. So that's sigma kk, and then v k j, right? And that's multiplied by I for the first qubit, let's say j for the second qubit.
So what is sigma aj?
Sigma, this is summation, right?
Okay.
So let me put tilde here to substitute to kind of see that it's not a summation sign. It's just some constant, such single value, right? And so then what one can do is to essentially break this summation into parts and write sigma k as a product with k vector for the first qubit and then k vector for the second qubit. And the first qubit k vector is sum over, let's say, I for the first qubit multiplied by u I k. And for the second qubit, it's a sum over j for the second qubit multiplied by v kj, right? So we present it as a product where this is the state for the first qubit, this is the state for the second qubit, right? Assuming that there is only a single k term. But if there are multiple k terms, then there will be sum over k as well. You could still do this, but there will be multiple products essentially. Okay. And this is how we can know whether the state of multiple qubits is entangled or actually is a very simple product state. Yeah.
That means that I entangle with J and J entangle with K, and then the I entangle with K.
Yes, in general, yeah, but there could be situation where I could be like if you have 3 qubits, presumably, I could be disentangled from J and K. That's the more kind of like this hybrid scenario where I is disentangled from J and K, and then J and K are entangled, or maybe they all disentangled, or they all entangled. Like the situation you describing sounds like they all kind of entangled. And yeah, I guess one other comment here is that you probably heard about the tensor networks that people use these days. And this is another approach to addressing the complexity of quantum mechanics, of many body physics, right? So if you have the situation where actually something that looks complicated in the form that is written as linear combination of products, you could try to use this Schmidt decomposition in order to see whether really there is a rotation of the single particle basis that makes it look more like simple, like in a product state, right? And or not. Or if you do studying, say, quantum dynamics, maybe the initial conditions are very sort of simple. Let's say they are well described as a product state. And then quantum dynamics, generally, if you want to use the like tensor product of spaces for all the particles, then the function, of course, will acquire the coefficients for all the basis states, and may look very difficult. But there are techniques where you propagate instead of this form in the tensor space, you're propagating sort of more like a tensor network that accounts for the fact that, well, there are some simplifications that can be done if you consider the right basis at every time, right? So that there is a compactification that can be made. And you probably, some of you may have seen the kind of the one simple illustration of this idea of getting the, I guess, the compression of the matrix is with images, right? So you could think of any JPEG image as a matrix with a little bit more structure. That number corresponds to the color or whatever, right? And so you could generally compress that image by taking the matrix, doing SVD, and seeing that actually not all the, well, like this sigma matrix is not containing all the all elements on diagonal which are significant. Some of them are small, and you could ignore the small ones, and therefore this form will have a kind of smaller number of elements to store. So that's one of the tricks, and it works with images essentially. But I guess, yeah, we should make a break, and then I'll get to the operators. Okay. Let me just pause the recording.
What we used to do during the COVID was that we record in a different computer. Because if we do that, then I can have both.
Okay, so let's resume. And the only thing that I wanted to, I guess, finish talking is that operators essentially that we need to deal with in the multiple qubit case. And there is another nice construction there that as like it's called Pauli group, right? It is indeed a group in a mathematical sense, and it's a, I guess, discrete group, and it has exponentially many elements, and the elements are just the tensor products of Pauli matrices for individual qubits. So here I superscript is the I qubit, and the Q here is I guess index that could be either 0 to 3, where 0 is identity, and 1 to 3 corresponds to X, Y, Z. And it's a tensor product. So as we know, when you work with the space of a larger number of particles, your function becomes like a function of in a tensor space, as we saw. But also the operators, they need to have now at least identity on all the elements, right? That we have, and these Pauli products, they are tensor, I guess, operators, tensor products of the single particle operators. And we have 4 to the n qubits of them, right? So it's a very simple combinatorics that we have n places, like number of words with the 4 letters in each. 4 possibilities for the 4 possibilities for alphabet is just 4 letters, 0, 1, 2, 3. Right, and all words are and letters in length, right? So these are the operators, and it turns out that again, like in a single qubit case, the only problem is that the number is now huge, but we can write any operator as before as a linear combination of all this coefficient Pauli product linear combination. And again, the coefficients could be obtained using this idea of inner product, but just defined for the for our operators instead of like our abstract vectors. And it is P n. Our dagger is not important because they are all Hermitian. Pn all divided by 2 to the n as dimensionality of space, right? Potentially one can do that. And again, if you are interested in the expectation value of this operator, you could always write it as a linear combination of expectation values of these Pauli products. We know all the Pauli products, expectation values that commutative operator, we can define the expectation value of that operator. Okay, so why do we call this group? We call this group because any Pauli, Pauli 1 multiplied by Pauli 2, it gives up to plus minus 1 and plus minus imaginary unit. Up to this factor, it gives yet another Pauli. Okay, so and that's considered yeah, essentially we have a group that they have a multiplication operator, and now every Pauli is a Hermitian. We could check that, and also because it also contains all the sigmas, they kind of inherit all the nice properties of sigma, which are, well, being Hermitian and being also self-inverse. So then it means that p squared is identity, right? So this property is there. And now what else these Pauli products will have is that turns out they are forming also Lie algebra. So Lie algebra, because any Pauli, if you commute with another Pauli, two Paulis essentially, they have only two choices. They either commute or anti-commute. So it's even nicer than just Lie algebra, because Lie algebra would say for Lie algebra all you need is like essentially the commutator of two Paulis being the sum of linear combination of other Paulis, right? But we have even better deal that we instead have this linear combination to be either 0 or if they anti-commute. In the case of anti-commutation, you could easily check that. Let's just do it together. P1 times P2, that's the commutator, minus P2 times P1, right? And if they anti-commute, then this could be turned into this one, but with a negative sign. So negative is positive. So you get 2 P1 P2 as a commutator. In the case of anti-commutativity of 2, it's anti-commutativity, right? And P1 P2, and that is well, product of 2, as we know from here. It's again some P from the set P3 up to constant, which is plus minus 1 or plus minus I, doesn't really matter. These 2 times that constant could be absorbed in the coefficient, and essentially the sum is very simple. It's just a single term or 0, right? So this is a commuting case, and this is anti-commuting case. Right, so that's why working with these Paulis is a pleasure, because the commutativity is very straightforward. And actually, the only big problem again is the number of these operators that we need to potentially deal with. Another point I want to make is a very simple rule to define whether we are in this case commutativity or anti-commutativity. Okay, and turns out, just to give you a very first very kind of mnemonic rule, that let's say we have sigma 1 for the Pauli 1, we have sigma 1, sigma 2, all the way to sigma n, and for Pauli 2 we have sigma 1 prime, sigma 2 prime, all the way to sigma n prime, right? So you always have for every Pauli like this, the statement I guess you can write every Pauli like this. And then in order to decide whether they commute or anti-commute, what you need to do is to look for corresponding sigmas, whether they are essentially commuting or not commuting. And we know for Pauli matrices, if one of them is identity, then it's always like there will always be commutativity. And if they are different letters, then they don't commute, right? And so what you do here is you count the number of non-commutativities, right? So let's say, for the sake of example, you have x1, x2 in one Pauli, and z1, z2 in another Pauli. So this don't commute and this don't commute. So you have two non-commutativities. And that means that they in total will commute. So as long as the number of non-commutativities is even, then 0 or like 2, 4, and so on, then they will commute. And if the number of non-commutativities is odd, then they will anti-commute. So for the odd situation, we could either do Z2 here, X1, Z1, X1, Z1, they don't commute, and then this do commute, so the odd number of non-commutativities. That will be anti-commuting case. Now, why is this working like that? You could simply realize that by putting this into the commutator form, this is a product of, let's say, sigmas, and this is a product of sigma primes. So the commutator of products will always be sort of one sequence p sigma prime minus another sigma, which another sequence p sigma prime p sigma. And then if you try to move this, say, through the sigma primes, if overall sign will be negative, then they will anti-commute. If the overall sign will be positive, then this will be just 0 and they commute. And when you move sigmas from here through sigma primes, of course, the sigmas of corresponding qubits, only them can change the sign. And essentially, we know that any sort of sigma like x with sigma y or other letters, they anti-commute. So when you exchange these guys with these guys for corresponding qubits, if the letters are different, then there's a change of the sign. And if there is an even number of such changes, then overall there will be no change of this sign, and it will be 0, right? So it's you could just see it for yourself by doing this simple algebra, and or just remember that if there is an even number of differences, then it's will be commutativity, odd number of differences, anti-commutativity. Okay, that's it's very simple. What else? Yet I guess another nice property one can use later would be that right. So technically, and we will return to this probably more in details later, but it's interesting that in order to generate all the Paulis, which is 4 to the n kind of operators, what you can do, you could take say sigma q I, all the single qubit Paulis, and you could take all the 2 qubit Paulis, right? So this is just a quadratic number in general, right? So this is corresponding to n qubits, and this is corresponding to n qubits square, right? And if you do all possible commutators between these elements of this combined set, you can generate all the 4 to the n Paulis. How it works is simply you could realize that yeah, let's say if you have say x1 and then in order to generate more Paulis, let's say x2, then you could do x2, okay, y2, and z3 commutator, right? So commutator of two quadratic Paulis will generate the product, because they anti-commute, simply because there is a one particular qubit where the letters are different. These, of course, commute with each other, right? So then we know this is up to the phase factor proportional to x1, z2, z3, right? So it will give you something non-trivial on 3 qubits, and so on and so forth. You could now generate 3 qubit Paulis, and I guess then go ahead and do some commutativity again, some commutations, and that will generate more and more and more, and so you will be able to generate all 4 to the n Paulis by repeating this commutation. Now, one thing I guess need to be very careful here. When I talk about this and this, I'm using slightly different notation, thinking about the q being only x, y, z, only non-trivial Pauli operators. I'm excluding identity because identity kind of doesn't really give much of substance. While in the original definition, to make it simple, I was using identity as well in this Q, but here I don't. And this is a nice property, which actually in the fermionic algebra, which we didn't talk about much yet, but for those who know, you could organize something with the fermionic operators like the single excitations and double excitations, something like this. And if you create all the possible commutators between the set of single and double, and then whatever will be produced by the commutators, you again do the commutators and so on and so forth. So you can go all the way to n electron, or it's like whatever actually number of orbitals, probably spin orbitals, operators. So again, these commutators will generate more and more terms, and that will be somewhat useful for the again understanding how to construct the unitaries, because after all, these are the generators eventually that we'll be using for constructing the unitaries. Okay, but this interestingly, this could be considered as the generators of the with respect to the multiplication, where multiplication is a commutator, right? Now, and we use the commutator to generate more and more sort of terms in the set. Okay. All right. So now it's time to finally finish the fermion qubit mapping. So we talked about how we can generate the qubit states and what the operators are. And let me remind you that we want to connect, say, our Slater determinants in the fermionic space to now two-level systems in the qubit space, and up and down, or zeros and ones again. And so clearly, if we want to create or annihilate electron, that would be raising lowering operators. Here I didn't, I guess, introduce that notation, but it's something that you've probably seen in the quantum mechanical courses. This is 1/2 of let's say xj plus minus I y j, right? So these are sigma operators, where these I'm skipping the sigma for the Pauli operators for the jth qubit. These are plus and minuses, and we know that if they plus and minus act on okay, let's say plus acts on the state of 0, you get the state of 1. And if the plus acts on the 1, then you get 0. Sorry, you just annihilate the state, right? So, and then with the minus it's the other way. 1 gives you 0, and then sigma minus acting on 0 will manipulate the state. So clearly, a creation annihilation will work like flipping essentially the orientation of the qubit, or going from one state to from 0 to 1. But the problem with that very simple idea is that fermions, as we discussed, they have this extra prefactor because they're coming from the states are coming from the state. Essentially, they are encoding Slater determinants, and you need to have the -1 into the power of occupations that we have before the fermionic mode that we act in. And because of that, essentially, our mapping becomes nonlinear. So it's not single Pauli operator is traded for a single fermionic operator, but instead we have these products of sigma z's, right? And so what these sigma z's are doing, they are making sure that if there is a, let's say, occupied fermionic mode corresponds to the qubit mode where qubits say up, so then sigma z will add -1 for that mode, right? So, and therefore we could now substitute A and A dagger by these products. Okay, and this is what Jordan and Wigner did in 1928. All right, so this was one of the first mappings between fermions and qubits, and it's sort of works like this. Now you could use this to write any fermionic determinant, Slater determinant. Let's say the example would be 1, 1, 0, 0. You could write it as a vacuum with creating the occupations on the second and first spin orbits. And in qubit form, that would correspond according to the mapping, say starting with the down all downs and then flipping flipping the qubits that for the first and second qubit, right? And so this is relatively straightforward. Now, this is for the states, and now we could do the operator that we had, electronic Hamiltonian, written in the form of products, right? So now we substitute every A and A dagger by our qubit form, right? And then it's like flipping again up and down, and we will get qubit Hamiltonian, which is completely isospectral, and it's a linear combination of Pauli products that we just talked about. And this is a Hamiltonian we will get, and we can work with that Hamiltonian on a quantum computer because it contains the qubit operators now. And if we find eigenstates of the qubit Hamiltonian, it will be the same spectrum as the electronic Hamiltonian.
And
Yeah.
hands up and down. This one is good and one is bad.
No. It's it's just a flip in the
Side.
kind of the qubit up and down. Yes, it's not up and down. Good or bad. All right. And I guess at this point, I wanted to talk a little bit more, like demystifying what sort of things could we see in the qubit Hamiltonians when we do this mapping. I already said it's the same spectrum, so that's nice. And also all the symmetries are preserved. So by this, symmetries are important in the solving eigenvalue problem. That's why we care about that, and constructing the state. Also, it helps to know that state that we're constructing has certain symmetries. But there are some kind of the terms that we're getting after switching to qubits, meaning that the Pauli products and the products of, if we compare Pauli products with the products of creation annihilation operators, they of course have different symmetric properties. What I mean by that, it's easy to see that, let's say, any a product of fermionic operators with the same number of creation and annihilation operators. They will commute with the number of electrons because the number of electrons stays the same. When you apply these products of A and A daggers, as long as the number of A's and A daggers are the same. But for the products of Pauli's, that's not the case anymore. So what I'm talking about is that any product like this, even if you make a product of products, doesn't really matter, as long as the number of daggers and number of non-daggered quantities is the same. So that will commute with the symmetry of the Hamiltonian, which is number of electrons. Remind you, the number of electrons is sum over A, P, dagger, A, P, from 1 to M, where M is the number of spin orbitals. So we have this nice relation. So no matter what part of the Hamiltonian we take, we have a conservation of the number of electrons. And this is not anymore true for a general Pauli. We could easily find the Paulis that will not commute with number of electrons. And it's easy to see because let's say if we have a Pauli that corresponds to just x1, then for the, let's say, x1, oh, maybe the easiest way would be, let me just tell you what sort of elements do we have in the Paulis that come out of the electronic Hamiltonian, right? So because there are some features that you kind of would expect, right? And some of these features are the following. If we take the say 1 electron terms, AI, J, there is always this TR, is time reversal symmetry here, right? So that what this means is that the Hamiltonian is real, and if it's Hermitian, so if you take AI, AJ, and then Hermit conjugated part will always be there, and there will be say single 1 electron integral coefficient. All of them are like these guys are real, right? And then we could see what sort of Pauli operators do we get out of the single electron terms. So it's a relatively straightforward exercise, and to make it somewhat simpler, let's take I and J, which are let's say close to each other, so that there are not too many Z's that will appear. And so in order to make it very simple, let's say it's a A2 dagger A1. So, and then plus a 1 dagger A2. So from this term, what do we get, right? And in order to see that, let's just write down x2 plus I, y2, z1. This is our A2 dagger. And then x1 minus I, y1. This is our A1, right? And correspondingly, we have A2, that is x2 minus I, y2, z1, just by Hermit conjugation. All the letters are, and you conjugate them, they give themselves, and just you need to change the I here. And then A1 prime and Y dagger will be x1 plus I, y1. All right, so after all this, if you put this all together, turns out only two terms after a lot of cancellations that I'm not going to bother you with. You could do it at home if you'd like. So the two terms that will survive is x1, x2 minus 2y1, y2. So these are the only terms. And the nice thing about them is that the coefficients are still real in general. And because the y's, they contain, I will remind you, the y contains the I. These are the y Pauli operator. In order to have the terms that are still real in the Hamiltonian, we have always even number of y's. Okay, so then the i's sort of cancel together because the even number of y's. And another feature, even if you go to the two electron terms, the number of xy letters is always either 2 or 4, because essentially the only time we get x and y's are from dagger and, well, non-dagger indices, and we have either 2 for the 1 electron terms or 4 for the 2 electron terms, right? So for the, yeah, we'll always have even number of x and y's, and there will be not more than 4. But the number of z's will be now potentially quite large, because if I and j are far away from each other, if let's say we have a 100 dagger A1 plus Hermite conjugated version. So in this case, we will have a lot of like z's here that eventually will end up in this strings here. You could see that I, for simplicity, took the case where they kind of cancel, but in general case there will be products that will essentially be there in this 1 electron and 2 electron terms. All right, so another note here is that actually for the 1 electron terms, for any Hermitian pair, we have again the same number of Pauli products, but for the 2 electron terms, we'll have already for let's say product like this, APQ, AR, AS plus Hermite conjugate version, we'll have 8 Pauli products, and essentially, if you, well, we don't deal here with 3 electrons and so on, but general formula, which will be useful for us later, it's 2 to the power 2n minus 1, where n is the, whether we're dealing with 1, 2, and so on electron terms. So you could see that if n is 1, then this is just 2, and then if you have n equals 2, it's already become sort of 8. Okay. So with that, I guess right. So the number of number operator that I was talking about before, one can check that it's not always conserving, and that's one thing that in Pauli products case one needs to live with. It's sort of something that we are trading for the fact that it's a single products which are Hermitian, okay, and they don't commute with a number of electrons. But overall, the Hamiltonian is still commuting with the symmetries. Okay, and the number of total number of terms is still n to the fourth because we're trading a single product by essentially like at most 8 products, right? So, oh, sorry, it's two products at least at most 8, right? So there is a constant prefactor in the 2 electron part, and therefore if we have n number of orbitals, then the number of terms in the fermionic Hamiltonian is n to the fourth, and then number of Paulis will be also proportional to n to the fourth. Okay. All right. So yeah, this is just a reminder for myself to kind of maybe note that when we talk about this spin symmetries, because qubits also could be considered, like sometimes people think about them as spins. So these are operators as z and s squares, electron spin operators, right? So they're not related to qubits, and they could be written in the second quantized form. Kilgacher is a nice derivation of all this, and you could check actually that all these operators, they commute with the fermionic Hamiltonian, even though it's sort of not trivial. But because Sx, Sy, Z, they don't commute with each other, they form again SU2 algebra. And then you need to select, and usually people select the orbitals so that the Hamiltonian sort of commutes with Sz and S squared, right? Rather than with all operators. Okay, now just to summarize this mapping between the fermions and qubits. So we have isospectral mapping, which is nice. So now we can work and with the second qubit version of the fermionic Hamiltonian. That's why we chosen the second quantization in the first place. There is a kind of price we paying, is that the mapping is nonlinear, and the situation is that in the terms like this, where the P and Q or I and J indices are far away, we're getting this products of Z terms, which well, quite large. Actually, there will be 99 potentially Z terms here, and then the Hamiltonian may look from the point of view of the we went from simple polynomial form to something which contains a relatively high number of terms in the expressions for each product, right? Monomials. And I looked at the Jordan-Wigner mostly. There are other techniques, there are other mappings, so-called Bravый-Kitaev. They are well described in this paper I put there by Peter Love, but the original motivation for Bravый-Kitaev mapping was that it essentially removes some of these long strings of Z's, and that people believed will be helpful for algorithms, but in near term it doesn't help. All right, so for fault-tolerant algorithms, it may be better. We'll talk about that. But for the near terms, which we will discuss next, it's not a big contribution. So therefore, I decided not to cover that in details. And the idea there is relatively straightforward. Now, in retrospect, is that you could encode the occupations, either 0 or 1, or you could encode parity of occupations that of the fermionic modes before the mode that you are considering. So that's another way to encode Slater determinants, right? So if you have a Slater determinant like let's say 1 1 0 0, so we know that this is the occupations that we are encoding here. But then there is another way to think about this is in terms of, okay, what's the parity? Is it of the, say, the previous orbital? So the previous orbital to this one will be no orbital, so it's a 0. And then for this one, the parity will be 1 because the previous one was occupied, right? And for this one, it's again 0 because it's now occupied, all the previous ones occupied. And you could continue like that. So this one is for the previous ones are occupied as well. And so encode effectively this as in terms of parities of occupation of the previous orbitals. And this is maybe less natural way to us to look at this, but in terms of the information that we're encoding, it's the same amount of information. But this amount of like this encoding allows to, when you go to the qubits, to produce instead of the operators with the long strings, produce the operators that have a kind of smaller number of strings, because the z's were there to make sure that there is a we signaling that the sign should be changed. But if now the kind of the encoding is different, then we don't need as many z's essentially, right? So that's the kind of intuition. Of course, I don't go into all the details. And Bravo and Kitaev, what they did, they tried to incorporate the best of both worlds. So for some qubits, they put the kind of the occupations, and for some they encode the parity of the previous. So it turns out that this mixed version is even better. Yeah.
This would especially help if you had it in canonical form, that you have like energy sorted, or like I imagine like that you have like your occupied space kind of, and then the unoccupied space, because then you would only have a very dense encoding.
Right. Yeah. So that for
like for a Hartree-Fock.
well, this is mostly to avoid kind of avoid the encoding of the Hamiltonian. That's what they worried about. And yeah, the Hamiltonian, of course, depends somewhat on the choice of the kind of what one particle orbitals they decide to choose. But generally, yeah, so they try to avoid essentially having in the Jordan-Wigner this strings of z's, and in this new mapping you don't need to have as many z's, and that helps when the z's become sort of expensive, but it turns out that it's for the near term it's not that big of a deal, right? So you could look at the again paper of Peter Love, where they explain it in nicely in details, and with numbers also how important this is for small molecules. And then for the variational quantum eigensolver that we will discuss next, it wasn't really found significant that we switch from Bravo-Kitaev to Jordan-Wigner or other way, right? And there is a actually even simpler maybe explanation for that, is that in variational quantum eigensolver approach that I'm going a little bit forward, we don't have really need to encode the Hamiltonian quantum computer, right? So in that sense, all that is immaterial in that case. It's only for the quantum phase estimation algorithm that will be sort of next. After the BQE, we need to put the Hamiltonian somehow into the quantum computer, but in BQE we don't. All right, and I guess at this point it's probably sure.
Can you repeat the thing with the parity, because I didn't understand. You said the first one.
Yeah, the first
the previous one there's nothing.
There's
You put
nothing.
a
Yes,
zero.
so you put a 0, and then the next one, the parity of the previous one is 1, right? So the parity is 1,
Yeah.
right? And then
then the third one.
the third one is if we sum how many electrons, right? The parity is the sum of all the occupations before. So 1 + 1 is 0 in the binary, right? So because it's -1
Okay.
to the power n, so right, yeah,
There.
and then so on and so
Yeah.
forth, right? Yeah.
I
Okay,
think we
yeah,
should
so
stop here.
yeah, we'll stop here and we'll start with the variational quantum eigensolver next time, okay? Okay.
And the recommended reading for